Line integrals. We start with a function of two variables, z equals f of xy, and a curve c. In general, the graph of a function of two variables is a surface in three-dimensional space, but we're going to restrict the graph of the function to that part which is lying above the curve c. So in this case, we just get a curve in three-dimensional space. If we choose two endpoints of the curve c and draw vertical lines from those endpoints of the curve c in the xy plane up until we hit the surface, we get a two-dimensional sheet in three-dimensional space. Our goal is to find the area of that sheet. Notice that if we take a point xy on the curve, then f of xy is the perpendicular distance from that point on the curve up until we hit the curve in three-dimensional space. That's part of the function z equals f of xy. Let's focus on just the curve for a second. And I have a picture of it here in the xy plane. We're going to chop that curve up into pieces. If we take the horizontal distance between two adjacent endpoints we just created, we will call that delta xk. And similarly, if we take the vertical distance, we'll call that delta yk. The straight line distance between two of those endpoints, we will call delta sk. What we do is we choose an arbitrary point on the curve between two of those adjacent endpoints, let's say ck, dk, and then we take f of ck, dk and multiply it by delta sk. That gives us an approximation to the area of the sheet restricted to that particular little subinterval. If we add all of those up, add up all the f of ck dk's times delta sk, we get an approximation to the area of the whole sheet. Taking the limit as n goes to infinity of this process gives us the exact area. And we call that the line integral over c of f of xy ds. Two other integrals that we will be interested in that do not represent an area, but come up in applications, are the integral over c f of xy dx, which is very similar. It's the limit as n goes to infinity of the sum of f ck dk delta xk. So instead of delta sk, we're just taking delta xk, which is the horizontal distances between two consecutive endpoints that we created. And similarly, we have the line integral over c f of xy dy, which we do the same computation, except we use delta yk. Now, in practice, we can compute a line integral by turning it into a definite integral. So starting with a curve c parametrized by x equals x of t, y equals y of t, where t is between a and b, then the line integral over c f of xy dx can be computed by taking the definite integral from a to b, f of x of t, y of t, times x prime of t dt. Similarly, the line integral over c f of xy dy can be computed by taking the definite integral from a to b, f of x of t, y prime of t dt. And finally, the line integral over c f of xy ds can be computed with the definite integral from a to b, f of x of t, y of t, times the square root of dx dt squared plus dy dt squared dt. Let's try an example. I'm going to put up those formulas I just shared with you so you have them in front of you. Now's a good time to pause the video, try these examples yourself, then resume the video to check your answers with mine. Let C be the quarter circle defined by x equals 4 cosine t, y equals 4 sine t, where t is between 0 and pi over 2. So the first one is the line integral over c xy squared dx. So we're going to change this to a definite integral. It's going from 0 to pi over 2 because the parameterization says that t goes between 0 and pi over 2. We're going to replace x by 4 cosine t. We replace y by 4 sine t. And since it's y squared, we get 4 sine t squared. And then remember that we multiply inside by x prime of t, which is negative 4 sine t, and then dt. We have 4 times 4 squared times negative 4, All that multiplies to negative 256, which we can pull outside of the integral because it's constant. And then we have sine t squared times sine t is sine cubed t times cosine t. We could do this with a very basic substitution. If u is sine t, then du is cosine t dt. So we just get u to the fourth over 4, or equivalently sine to the fourth t over 4. 4 goes into 256 64 times, so we get negative 64. The sine of pi over 2 is 1, and the sine of 0 is 0. So we get 1 to the fourth minus 0 to the fourth, which is just 1 to the fourth, or 1. So the final answer is just negative 64. Next one, the line integral over c xy squared dy. So the first part is the same, the integral from 0 to pi over 2, 4 cosine t, 4 sine t squared. But this time we multiply by y prime of t, which is 4 cosine t dt. Pulling out the constant, we have 256, integral from 0 to pi over 2 sine squared t cosine squared t dt. Now we have a couple of options with how to do this integral. We could use the power reducing formula twice, once for sine squared t and one for cosine squared t. But in this case, there's a little bit of an easier way. We could use the trig identity sine 2t equals 2 sine t cosine t to rewrite sine squared t cosine squared t as 1/4 sine squared 2t. Notice here that sine squared t cosine squared t is the same thing as the square of sine t cosine t. I'm replacing sine t cosine t with sine 2t over 2, and then I have to square that. So I get sine squared 2t over 4, or 1/4 sine squared 2t. Okay, pulling out the 1/4 and multiplying by 256 gives 64. And then I'm going to apply the usual power reducing formula to sine squared 2t to get 1/2 times 1 minus cosine 4t. 2 times 2t is 4t. Okay, pulling out the half and multiplying by 64 gives 32. Antiderivative of 1 is t. Antiderivative of cosine 4t is 1/4 sine 4t. And we're going from 0 to pi over 2. Plugging in the 0 gives 0 minus 0. Plugging in the pi over 2 gives pi over 2 minus 0. So we just get 32 times pi over 2, which is 16 pi. Okay, and finally, the integral over c xy squared ds. Again, the first part is the same. We get the integral from 0 to pi over 2, 4 cosine t times the square of 4 sine t. And then we have to multiply by the square root of dx dt squared plus dy dt squared. So that's the square root of the square of negative 4 sine t plus the square of 4 cosine t. That is just the square root of 16 using the Pythagorean identity as usual. And the square root of 16 is 4. So that is where that 4 comes from there. Pulling out all the 4s, we have 256. And inside the integral, we're left with cosine t sine squared t dt. We could do a simple substitution here. U equals sine t, du is cosine t dt. So that becomes u cubed over 3, or equivalently sine cubed t over 3 from 0 to pi over 2. And once again, plugging in the pi over 2 gives us, well, the sine of pi over 2 is 1, so that's 1 cubed, or just 1, and sine of 0 is 0, so we just get 256 over 3. Let's try some more examples. Once again, pause the video and try these examples yourself, then resume the video to check your answers with mine. Let C be the following curve. C is defined by the function y equals x cubed, where x goes from negative 1 to 2, and compute the line integral over c 2xy dx plus x squared dy. In this case, since y is a function of x, we can use x itself as the parameter. When we change the line integral to a definite integral, we have the integral from negative 1 to 2, because x is going between negative 1 and 2. 2x, we leave x as it is. We replace y by x cubed, and we leave dx as it is. And then once again, we leave x squared as it is, but then we have to multiply by the derivative of y, which is 3x squared dx. So we have 2x to the fourth dx and 3x to the fourth dx. That adds up to 5x to the fourth dx. When we integrate, we get 5x to the fifth over 5, or just x to the fifth from -1 to 2. So that is 2 to the fifth minus -1 to the fifth, or 2 to the fifth plus 1, which is 33. Next one, find the area of the surface extending upward from the circle x squared plus y squared equals 1 in the xy plane to the parabolic cylinder z equals 1 minus x squared. Okay, in this case, we want the line integral over c, 1 minus x squared ds. So we start by parametrizing the circle as x equals cosine t, y equals sine t. T goes from 0 to 2 pi. So ds is the square root of the square of dx dt, which is negative sine t, plus the square of dy dt, which is cosine t. And since sine squared t plus cosine squared t is equal to 1, we just get that ds is equal to dt. So now we change to a definite integral. T is going from 0 to 2 pi. And in place of x, we put cosine t. So we get 1 minus cosine squared t. And ds we just found is equal to dt. Using the basic Pythagorean identity, we can replace 1 minus cosine squared t by sine squared t. We can then use the usual power reducing formula to rewrite sine squared t as 1/2 times 1 minus cosine 2t. When we integrate, we get t minus 1/2 sine 2t, a little substitution there. U equals 2t, du is 2 dt. That's where the extra 1/2 comes from in front of the sine 2t. When we plug a 0 or a 2 pi into sine 2t, we just get 0. So we just get 1/2 times 2 pi, which is pi. Let's do one more example. Once again, pause the video, try this example yourself, and then resume the video to check your answer. Evaluate the line integral over c, y squared dx minus x squared dy on the closed curve c shown in the figure. Let me just mention that that little circle on the integral symbol there is just being used to indicate that we're integrating over a closed curve. It's not necessary to have it there, but very often authors will draw that little circle whenever we have a closed curve. They may even put a little arrow to indicate the direction of the curve, whether it's going clockwise or counterclockwise. Okay, in this case, our curve is defined with 3 pieces. There are 2 line segments and a parabolic path. So we're going to want to do each of those line integrals separately and then add them all up. So I'm going to label them as C1, C2, and C3. Let's start with the line integral over C1 of y squared dx minus x squared dy. Well, for the curve C1, y is equal to 0, right? Because that curve lies along the x-axis, which has equation y equals 0, and therefore dy is equal to 0. So in this case, we just get the integral from 0 to 2, because x is going from 0 to 2, of 0 squared, because y is 0, dx minus x squared times, again, 0, because dy is 0. So we just get 0. So this first line integral along C1 does not contribute anything to the answer. Next, let's do the line integral along C2 of y squared dx minus x squared dy. In this case, C2 lies along the line x equals 2. And since x is constant, dx is 0. Now, y is going from 0 to 4 here, because when x is 2, y is 2 squared, which is 4. And we have y squared times 0, because dx is 0, minus 2 squared dy, because x is equal to 2. So we just get -4 integral from 0 to 4 dy, which is -4y from 0 to 4, or -4 times 4, or -16. Finally, let's do the line integral over C3 y squared dx minus x squared dy. On C3, y is equal to x squared. We'll use x as the parameter, and we see that dy is 2x dx. So since the arrow is going from right to left, x is going from 2 to 0. So that's why the limits on the integral start at 2 and then go to 0. Y is x squared, so y squared is x to the 4th. So we have x to the 4th dx minus x squared, and dy is 2x dx. So we have the integral from 2 to 0, x to the 4th minus 2x cubed dx. Using some power rules, we get x to the 5th over 5 minus 2x to the 4th over 4, or x to the 4th over 2, from 2 to 0. When we plug in the 0, we just get 0. When we plug in the 2, we get 32 fifths minus 16 over 2, but we're subtracting that. So I flipped it around and wrote it as 16 over 2 minus 32 over 5. So that's 16 times 5 minus 2 times 32 over 10, which can be reduced to 8 over 5. Finally, the line integral over c y squared dx minus x squared dy is the sum of the three answers we just got, 0 minus 16 plus 8 fifths, which comes out to negative 72 over 5.